we start with an introduction of the company COMPREDICT and the world into virtual sensors. Afterwards, Guillaume will present you our solutions for hardware replacement. Typically, we get a lot of questions regarding our virtual sensor technology, so we will take some time to guide you through the hottest FAQ we regularly get for the topics today, followed by what you can take away of today's session of roughly 30 minutes. So your key takeaways of today. And last but not least, how you can continue your journey with us, with COMPREDICT and with the world of virtual sensors. So starting with the introduction of our company and of virtual sensors. The big question is, what is a virtual sensor? So in the end, it's a pure software solution with the same capabilities of a physical hardware sensor without its downsides. How do we do it, or how can a virtual sensor be realized in the automotive industry? Well, each car has many sensors available. They are there for functional safety reasons or for proper controls, and you won't get rid of them. These sensor data are typically distributed throughout the vehicle via CAN or Ethernet or any other technology. And we, for virtual sensors, access these data to realize virtual sensors. How we do it? It's split in two domains on our side. We start with our so-called automotive domain expertise, which is basically physical relations and vehicle dynamics constraints between the vehicle signals to give a certain robustness to the virtual sensor. The other point is data science and machine learning. So these huge amount of data, of course, need to be processed in a proper way. And with machine learning approaches, we can increase the accuracy of the virtual sensors a lot. And that's why these two approaches can completely generate new opportunities in the vehicle in terms of new SDV capabilities with high computing power, replacing hardware where we are focusing on today, or even to enhance your after-sales business, what we explained to you in the last webinar. So what is COMPREDICT as a company? You can see on top, backed by Toyota, trusted by Renault Group. Trusted by Renault Group means we are deploying our first virtual sensors in series production by next year in up to 10 million vehicles across the entire group. Not only Renault, but also Alpine and Dacia. Here we use the technology for tire and brake wear, which we explained in our last webinar in the after sales. As a recap, we are a fully software-based company, which means we are not a traditional tier 1 supplier supplying any ECUs plus software, but only software as a service and as an integration package. We are working together with 10 OEMs across various countries over the entire world, and we are compatible with any software-defined vehicle in the market. Coming backed by Toyota Woven Capital. So Toyota and Woven Capital as a venture capital investment was searching the entire world for new technologies in the automotive industry and found us here in Darmstadt as a software startup for virtual sensors. So their target was to increase their investment in this domain, and they invested into us in our last Series B funding last year, 2024. Our other partners, you can see it, mainly working with integrators and software companies to being able to deploy our virtual sensors in the automotive market. And of course, we need to gather lots of vehicle data and taste data. Here we have a close collaboration with UTEC in France, which is also caused by our close relationship with Renault in France. So COMPREDICT has three main application areas for the virtual sensors. Last time in the webinar, we talked about the after-sales business. Our next webinar will be about new SDV capabilities, but today we will focus on actual hardware replacement and redundancy solutions with the benefit to lower the total cost of ownership, reduce hardware dependency, or being able to increase the safety of the vehicle and of functionalities with virtual redundancy if you don't want to get rid completely of physical sensors. And the possibilities for these replacement and redundancy sensors, I will hand over to our product manager, Guillaume.
Thank you, Moritz. Thank you very much. So in the following part, I will mainly discuss about our hardware sensor solution and how you can replace hardware with our software solution. So first of all, let's have a quick look at our whole portfolio regarding hardware replacement. So on the left-hand side, you can see that we have today 6 different solutions of virtual sensor, of hardware replacement virtual sensor, headlight leveling, motor temperature, brake and tire temperature, tire pressure, and suspension displacement as well. Today, we will mainly focus on 2 of our solutions. The first one is headlight leveling, and the second one is tire pressure. So it's from COMPREDICT side point of view, 2 hot topics due to the regulation and also due to the cost reduction that are facing all the OEMs right now. So obviously, we have 2 main benefits of our hardware replacement virtual sensor solution. The first one is cost saving. By replacing hardware, for sure, you are reducing the BOM, the bill of material of your vehicle, and then you have cost saving, and you can reduce your cost at scale regarding the all production that OEM have. The second main benefit of our hardware replacement virtual sensor is the fact that it's 100% software. Then you get rid of hardware sensor and you eliminating all the hardware sensor wear and tear, and so no failure due to any hardware. So that's the 2 main benefits that we have regarding our hardware replacement solution. But now let's go more in detail on our headlight leveling solutions. So as you may know or not, a new regulation is coming in September 2027 regarding headlight leveling, and automatic headlight leveling will become mandatory for all the new passengers vehicle after this deadline. What does it mean concretely regarding the actual solution that you can find in the market? First, it means that the traditional manual leveling solution that you have via a dashboard switch or even via a screw directly on the headlamp should be replaced, because you should get automatic solution in September 2027. So all those cost-efficient solution could not be put in any new vehicles and then have to be changed by an automatic solution. The issue is that today, the automatic leveling solution are mainly do with hardware, with costly hardware sensor, especially a RIDE 8 hardware sensor that, depending on the different OEM and also depending on the different solution that you use, are in only the rear axle or on both front and rear axle. And today, based on the different customer projects we already have and based on our knowledge, we know that for one to do hardware sensor, RIDE 8 sensor, the cost per vehicle could reach 20 euros, including the hardware, but also the wire, the assembly, and everything directly related to the hardware sensor. So, which is a huge amount of money from OEM point of view. Then, in response to this new regulation, COMPREDICT, we have developed an headlight leveling virtual sensor solution that is calculating the pitch directly of the vehicle. It means that the pitch, which is the main input for headlight adjustment in static and dynamic way, is the output of our solution. As I already said, our solution is 100% software, meaning that we don't need any hardware anymore, And we are only using, as Moritz explained in the first part, we are only using some existing vehicle signals that you can find in any vehicle, and you don't need any additional hardware. Also, one of the main takeaway that we can have for this solution is that today it is working statically, but also dynamically. By static, I mean that our solution is working in all the different regulation case defined in the new regulation of 2027. It means that, for example, for an M1 vehicle, our solution is working in all the 5 different load cases that you can find in the regulation with a pretty good accuracy, or at least with the accuracy that permit us to pass easily the regulation. And in the second point, our solution is also working dynamically. It means that in normal driving condition, where like acceleration, for example, braking or slopes or common driving condition, our solution is working perfectly fine dynamically and permits to adjust dynamically the headlamp, with an accurate pitch angle calculation. And finally, by replacing the hardware that you have in your vehicle, you can easily save up to 20 euros if you have one ride height sensor on front and one ride height sensors on the rear. So now, just a quick overview of what we call our virtualization approach. It means that when our solution is implemented in the vehicle, so when it's deployed in vehicle in any ECU, by using the different signals that you can find in all the different vehicles, first we can have a prediction, we can accurately predict the static load changes first. Then we can have the prediction of the dynamic suspension travel on wheels, and based on these 2 different calculations, then we are able to estimate the vehicle pitch angle. And as I already said, this pitch angle is the main input to as in the main target value for the headlight adjustment at the end. So it's quite an interesting approach and a very easy approach, very simple approach, yes. And here, just we can focus mainly on some first results that we have. Here you can see, firstly, the static specification of our headlight leveling solution. So in the plots, you can see 3 different load cases that you can find in the regulation. The first one, which is the A cases, so in the orange A box, is the first load case of the regulation, is the driver only. So you can see we have loaded on the first seats of our demo vehicle, which is the reference for our first estimation, for this estimation and this calculation. So we are loaded the first seat with 75 kg. Then the second load cases is in the C orange box. So it means that we have loaded all the different seats with 75 kg. So it's the third load case of the regulation, and the last one is the final load case of the regulation, when we load the driver and also when we put the maximum load on the trunk. You can see in these results that the accuracy, the root mean square error, which is the accuracy of our model, is quite good. It's less than 0.05% for driver load case only, and less than 0.15% for the 2 other load cases, which is quite accurate and quite good, and which permits our model and all the vehicles to meet the certification criteria easily. You also can see that in the transition phase, it means that B, D, E, and F as our transition phase when we are loading and also unloading the vehicle, to simulate the different load cases and then to get the estimation of our virtual sensor. You can see that the accuracy is quite good even in this transition phase, meaning that our model is calculating quite fast the pitch angle and is estimating in less than 1 second the pitch angle of the vehicle between the different load case, which is quite sufficient, regarding the static, from static point of view. We just to finish on the static specification, you can see some minor deviation that are remaining, in D and also in C phase that we are working on, because we are continuously improving our model and working on it. And so all these minor deviation are now under control. Yeah. So it was the static specification, and now if we go more in detail in the dynamic one, you can see there are 4 different plots, and you can see, before going much more in detail of the RMSE, of the accuracy, you can see that the trend of the calculation trend of our estimation is quite good regarding the reference. So you see in the 4 plots, the reference is in blue and our calculation is in orange. You see that the trends are well identified, and that all the different peaks and all the different parts, are well estimated. The two up plots, when you can see normal driving and braking acceleration, that we consider as common driving cases. For those 2 different cases, we have an accuracy of less than 0.50%, which is quite good, and which is quite sufficient, regarding all the different the main driving condition that we face in the normal life. And the 2 last plots show driving slalom and driving on bumpy road, when we can see some minor deviation, especially during rapid or high frequency events. But for those 2 different dynamic conditions, we don't think that it's quite an issue, because today, regarding the performance of the actuator that we have to adjust the headlamp, those rapid or high frequency events are too quick, to be able to capture and by the performance of the actuator. And so what we see is that the accuracy that we have for the normal driving and braking acceleration are quite enough in dynamic condition for headlight adjustment right now. So in a nutshell, regarding headlight leveling, from static and dynamic point of view, we see that our model has a quite robust performance across different maneuvers, and also from static regulation load case point of view. The RMSE is globally under 0.15% in all the interesting use case, which is quite sufficient, to have a performance solution right now. And we only see some minor deviation, minor deviation in some edge cases, which is, from our point of view, not an issue for headlight leveling adjustment right now. So now, let's go on the tire pressure virtual sensor solution. So today, as you all may know, there is a regulation since July 2007 that asks for mandatory tire pressure warning for all new passenger vehicles. So tire pressure warning, TPW, is just a warning that warns the driver when you have a deflation of a tire, or what we call a diffusion of a tire, means that all the tires are deflated at the same time. But from a regulation point of view, you don't need to have, the regulation is not asking for a real tire pressure value, and is not asking to know if you face the deflation or a diffusion case, to know which tire is it. So TPW, tire pressure warning, is just for the regulation right now. But there is also another solution in the automotive world, which is called tire pressure monitoring system. When you are using tire pressure sensors, so one on each wheel, and that is a value for each tire in real time. And the main benefits of this solution regarding tire pressure warning is that you are able to ensure a proper inflation of every tire, of each tire, and then you are increasing safety, because you don't need to wait for a warning when your tire is deflated by more than 20% to have an alert. And also this solution is more cost efficient because you are saving fuel and you are saving your tire by driving with the right tire pressure, And this tire pressure monitoring system solution could be an hardware replacement option, because if you are able to give the tire pressure and the real-time tire pressure value for each tire without any hardware sensor, you can also get a high and a huge cost saving. And at COMPREDICT, that's what we are able to do. So today, our tire pressure monitoring system virtual sensor is not just tire pressure warning, it is the first direct TPMS virtual solution, meaning that without any hardware, and so by removing all the TPMS sensor that you can find in all the four wheels of the vehicle, we are able to calculate a real-time pressure value for each tire, and then be able to save up to 15 euros per vehicle by removing the hardware sensors, but also the receiver and everything related to those hardware sensors. So our solution today is the only direct solution that is able to calculate real-time pressure value virtually without any hardware sensor. And as I already said at the very beginning of my speech, this solution is 100% software, and so you don't face any failure related to hardware sensor, wear, or tear. And then, to finish this quick overview of our hardware sensor solution, let's have a quick look at the performance specification of our tire pressure virtual sensor. So on the left-hand side, you can see during some thousands of kilometers, the tire pressure measurement versus the tire pressure estimation of our virtual sensor. So in orange, you can see the results of our virtual sensor, and in blue, the measurement. You can see that our virtual sensor is able to estimate the current tire pressure for each tire in bar with an accuracy of plus or minus 0.2 bar in common driving condition, which is quite, which is quite the same accuracy that you can find in any hardware solution. And one of the main points is that our solution is able to fulfill the regulation requirements by detecting puncture of any tire. So by puncture, we mean a drop of 20% of the nominal pressure in any tire. Then we are able to detect which tire is it. And we are also able to detect if there is a diffusion case, meaning that all the tires are deflating by more than 20% of their nominal pressure. So that's the main advantage and benefits of our tire pressure solution. And that's the only solution in the market that is able to do all of this in a virtual way, so virtually. And then I think I will hand over to you, Moritz, just to get answer for the hottest FAQ.
Sure. As you now heard about our technology, there are a lot of questions, how it works, what are the boundaries, and therefore I will take the next few minutes to dive a bit deeper into the FAQ we regularly receive from customers regarding our technology. So first question that we regularly get is what kind of data is required to run the virtual sensor. So as already explained in the beginning, we only use readily available CAN signals that are in the vehicle, mainly focusing on wheel speeds, accelerations, deceleration values. And these signals that we use, we split into required signals that there's no point for discussion. If these are not available, a sensor deployment is not possible. And on the other hand, optional signals that shall increase the accuracy of the virtual sensor. The second question that we usually get is the minimum sample rate of the signals for our input. Here, it heavily depends on the sensor, but we say typically 10 to 100 Hertz of CAN frequency is required. But in modern vehicles, also this is usually no issue, as on the standard CAN speed is typically from 100 to 200 Hertz. So there we usually don't face any issues for the integration. The higher the requirements to the dynamics, as you can see, the higher must be the sample rate of the inputs. It's just physics that are behind, and I guess every one of you can understand that. The question we also get is what technology we use for the virtual sensor. Is it machine learning? Is it model-based? And here, as already explained as well in the beginning, we do a combination of model-based and machine learning. And our core competence is the automotive domain knowledge and the machine learning as a combination. And to calibrate this combination to your fleet is our core strength in the company where we are coming from. Another question we also get is, where's the virtual sensor running? Is it offline? Is it in the car? And we say our virtual sensors are in-car sensors. That is, are actually there, in this case, to replace physical sensors and are no cloud and offsite solutions. But there is no additional ECU required that we also don't deliver. So our virtual sensors can be deployed and integrated into existing ECUs, especially with the upcoming trend of more powerful ECUs that are even able to handle the processing requirements of our sensorics. Based on that, the next question is usually how many calibration versions per virtual sensor are required for various vehicle variants. And here, the answer we have to give you is always, it depends. It mainly depends on the influential vehicle design parameters, especially for which domain and which sensor you want to replace. If the basic design is equal, then the probability is quite high that you don't have to have various or two different vehicle or sensor calibrations, but you can compare it to each and every traditional software that's running in the vehicle and the typical variant management that established tier 1 suppliers also have to face in terms of variants within one vehicle platform. The last question about licensing for our virtual sensors. Of course, financial aspects also need to be covered, at least partially in this webinar. And here we say it is as a traditional hardware sensor on a per vehicle basis. If you buy a physical sensor, you also have part costs of per vehicle, and this is the same approach we are using for our hardware replacement virtual sensors. But you have very attractive cost savings, not only due to a lower piece price, but also due to a much lower TCO, because you don't have to care about additional wiring, you don't have to care about sensor wear or failure, and about possible recalls if you figure out that your physical sensor has any issues. Virtual sensors, as already said, pure software solutions, and updates are also purely based on software capabilities and also over-the-air updates. So I hope this brief introduction into the FAQ gave you a better overview and answered the most of your questions, so that I can hand over again to Guillaume to go into more financial stuff.
Yeah, thank you, Moritz. So to finish this webinar, what you can take away, mainly two things. I think there is two main things to take away. The first one is that with our virtual sensor solution, the OEM can save millions at scale by replacing hardware sensor. This is the main point and the main benefits of our solution. The second one is that our software solution are only using existing vehicle data that you can find in any vehicle to replace legacy hardware. It means that our solution, as Moritz already said, could be implemented in all the SDV vehicles, in every vehicles with data, you know, and which with our solution, you can save millions at scale. And just to finish with simple business case, then here you can find the Headlight leveling business case. So on the right hand side, you see the cost saving that you could have by replacing the hardware sensor, and so especially the right 8 sensor. So as already said, from 5 to 7 euro per hardware sensor and 2 to 3 euro for wires, assembly, and everything related to the hardware sensor. It means that for one sensor, you can save up to 10 euro per vehicle and 20 if you have two right 8 sensor in your vehicle. And on the other hand, you just need regarding the integration project on the time and you just have to pay on the time and material basis for the integration. And as Moritz said, the licensing cost is less than 30% of hardware solution. So making the calculation on one model, which is like 100K units per year with 2 hardware sensors replaced on the 5-year production, you can save up to 7 million euros over the production period, which is a huge amount, and which is only permitted by the fact that our solution is fully replacing hardware. So thank you. Now I will hand over to Moritz for the conclusion of our webinar.
Yeah, I hope that with this webinar, we could again raise your awareness of possibilities for integration of additional software instead of hardware in the automotive industry. And if you have concrete use cases or application areas for your virtual sensors, we will be happy to talk to you, to discuss your use cases, and to find solutions for your approaches. At the bottom of this slide, you can find our contact information either via website or via mail. And we are quite active on LinkedIn, so here you can check out our latest activities that we regularly post. So the QR code directly will guide you there. As I said in the beginning, it is a webinar series. It is now the second webinar of the series. The first one was in September. You can watch the recording via following the QR code at the bottom. And the next one will be mid of November, where we dive deeper into new SDV capabilities that can be realized with our virtual sensor technology. Please, I would ask you also here to follow the QR code and directly register for the event. So coming to an end of this webinar, I want to thank you for your participation, and I hope we see each other again in November. Thank you and goodbye.
Thank you. Goodbye.